we talk about identities, it's a statement of equality between two expressions that is true for all values of the variables for which the expressions are defined. I really don't know how to simplify that anymore. We're going to prove statements are identities. They're going to give us some complicated trigonometric expression equal to some other complicated trigonometric expression, and we have to prove that that's true. Well, they're going to give us some identities that are true to begin with. Some you've seen already, some that are new. And then we're going to use those facts that we know to be true to manipulate our expressions to get them to the form to which the left side is equal to the right side. Okay? I said complicated. Sometimes they're very simple looking. And we have to make them complicated looking to make them equal. Sometimes they're complicated looking. We need to simplify them. Okay? To me, it's a big puzzle. And I know I'm weird compared to the rest of you, but I actually really enjoy working on them. Sometimes I don't get the answer. Sometimes I don't solve every puzzle I try. Okay? But I still enjoy trying to use what I know to manipulate these expressions into something that's equal to the other side. So trigonometric identity is an identity involving trigonometric expressions. And then I want to remind you here, reminder, it only takes one counterexample to prove something is false. So it only takes one counterexample to prove an equation is not an identity. But to prove that it is true, you must show that it's true for all values of the variables. Okay? So here are some identities that you've seen already, the reciprocal identities. Sine theta equals 1 over cosecant. Secant theta equals 1 over cosine. Cosecant equals 1 over sine. Cosine equals 1 over secant. Okay, tangent equals 1 over cotangent. Cotangent equals 1 over tangent. Those you've seen before. This tangent one, you've seen before. Tangent theta equals sine theta over cosine theta. I've probably not shown you the cotangent one, but it should make sense to you. Cotangent's the reciprocal of tangent. So instead of sine over cosine, we'll have cosine over sine. I think you should put all these on a separate sheet of paper. Okay? And keep your identities together. On the test, I will allow you, and I'll show you which ones you have, but these are all part of it. I will allow you to put all these on a separate sheet of paper that you can use on the test. So I would recommend you taking the moment now, copy all these down, and put them on a separate sheet of paper, one that you can have on the test. I'm going to pause this while you copy.
You don't want to miss.
Let me explain what the circle means here, and that's where these Pythagorean theorems, or Pythagorean identities come from. Remember this cosine here, this line here, this line here that the cosines point to is the x value, right, of that triangle? And the sine is the y value of that triangle. And so if you look at this picture as x and y, then x squared plus y squared would equal 1 squared. We're on the unit circle. And so that means cosine squared plus sine squared is equal to 1. So that's where that comes from. And these other two, the tangent squared theta plus 1 equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. Those are derived from this top one here. And so they've done the work of that. They're saying, hey, these are all true. You don't have to prove these true. You can accept these to be true. We could prove them if we wanted to. But, and we may in some of our practice and stuff. But the fact is, you're going to use these facts to help you prove other identities. Okay? these are upcoming lessons, but just, we've got our cheat sheet out now. We're putting this onto, copying onto a separate sheet of paper for the test. So let's put everything on there that we're going to use, and then you'll have it to refer to as you're doing your work.
So this is.
Don't lose it, and don't add anything else to it. What we had on that last page plus this will be the only ones you can use on your test. Then realize these top three here are already on your paper. But the sum and difference identities, the double angle identities, and the half angle identities we'll cover later.
Ones that, under the ones we already know.
These are called sum and difference identities. Adding two angles. Okay, I'm gonna pause that so you can copy the rest of them. Just to make sure, if you're copying this at home, the plus and minus, the minus plus are written the way they are for a reason. Do not switch them around. Do not mix them up. It's there's a significance to it. When we're teaching that lesson, we will explain it. So moving on.
You want these on our actual notes?
These are symmetry identities.
These on our actual
You can keep these on your, I've forgotten about these, but they can go on your test notes also. They won't be used that much. So having them lasting on the bottom is not a bad thing. Okay, so I'll pause while you copy.
Yeah.
I'm not sure why I only numbered the first 5. There's 8 of them there. And you may put them on your test cheat sheet. And then to switch this over to radian measures, simply switch the 180s with pi and the 360 with 2 pi.
You want us to read them?
So last two opposite angle identities, the sine of the opposite of A is equal to the opposite of sine A, and the cosine of opposite of A is equal to cosine of A.
Is this one cheat sheet?
It can go on your cheat sheet also. Your cheat sheet also. Be careful how we say that. Might be
Is that
some
as
naughty
negatives?
words. This is an identity.
We're going back to our notes now.
Is this like in our notes?
These are examples of our identities. So we're on notes now. These are not cheat sheet material. Example, we're using number 20 as an example. Copy this down. Trent, stop talking. Copy this down. Now I have not looked at this. I've not I'm not prepared, how my plan of attack for this. I don't have it done in my notes. I do these things like this on purpose. Sometimes I might stop and struggle and pause the recording while I think it through. Okay, I do that on purpose because I want you to realize sometimes they're tough, sometimes you have to think about it, and I want you to see my process of dealing with it. Okay? Sometimes I look at them and I have a good idea, and other times I don't. So in general, when I take a problem like this, I look at this side, and because of the squared, I see that to me is more complicated than this side. Okay? But to be honest, as I look at the right side a little closer, I'm going to probably manipulate that also. So the first thing I'm going to do is I'm going to go back to my my cheat sheet, and I'm going to look at my trig identities, and I see that this one right here, sine squared theta is equal to tangent squared theta plus 1. So if I go back to my problem here, I'm sorry, I said sine squared theta. I meant to say secant squared, which is what it said. This is equal to tangent squared x plus 1 minus 1 is going to equal cosine x over, would you agree that cosecant is the same as 1 over sine? Okay. And so now when I look at this side over here, tangent squared x plus 1, are the parentheses important?
Yes.
No, they aren't, because all I'm doing is adding and subtracting here. I put them in originally just to show you that where this was, the secant squared was, I replaced it with tangent squared plus 1. But they're really not important. So what happens to my plus 1 minus 1? They cancel out, so I'm left with tan squared x is equal to gosh, I just look at that right side, I feel like I copied something down wrong. I'm not seeing exactly where it goes. Cosine x divided by 1 over sine is the same as times sine over 1, right? And so I get tan squared x is equal to cosine x sine x. Okay. That's an S for cosine. That's a squared.
Can you break the tangent up into sine? Sine over cosine.
Yeah, you can.
Sine over cosine.
But it's squared.
When I do that, I get sine squared. I was looking at that, but I still have squared, so I still have a fraction. I look at the other side. Let me pause a second. I'm sorry, I got a little ahead of myself. We're not going to be successful on this method because it's actually not true. And they want us to prove it's not true. Once we read the directions, they said to find a counterexample. And so what I would do then is I would pick a nice number like a 30, 60, or a 45, something that we know, okay? 45s would kind of get us in trouble because do you agree that the sine of 45 and the cosine of 45 are the same?
Yes.
And so because of that, sometimes we could get in trouble using it as an example. So I'm going to try 30. So secant squared of 30 minus 1, is that equal to cosine of 30 over cosecant of 30? Now, we turned all of this into tangent, didn't we? Squared. And so we did that work. I'm not going to just throw it out. And we turned this into cosine times sine. And so again, I'm not going to just throw that out. This here is tangent squared plus 1, and the plus 1 minus 1 cancels. And so we're left with tangent squared. And so the tangent of a 30-degree angle, 1, 2, square root of 3, and this is the 30. The tangent is opposite over hypotenuse, so it's 1 over square root of 3. We normally wouldn't want to leave it that way, but because it's squared, it doesn't matter. Set that way up. And so this turns into 1/3. Square 1 is 1, square root of 3, I get 3. And on this side, cosine of 30 is square root of 3 over 2 times sine 30, which is 1 over 2. And so that gives me square root of 3 over 4. Is 1/3 equal to the square root of 3 over 4?
Yeah.
No. So my counterexample is 30 degrees.
Can you use just like 90?
You could. Again, 90 gets us in trouble sometimes because when we're dividing, if our 90 is on the bottom, we get an undefined number, which might create us some faults. You understand what I'm trying to say? Not saying it very clearly.
But you could still do it for some of them if you could.
Tomorrow, when we start talking about 7.2, then we'll have some rules for verifying identities. And that's what got me realizing that I was doing the wrong thing today, is because I realized that I didn't have my rules for you. And you won't have to verify until I give you rules. So I started getting ahead of myself there. I apologize for that. But this is all they're looking for.
Second quadrant?
Yeah, because the angle is between 90 and 180, and we're in quadrant 2.
And that's the only way to.
We're over here, okay? And so that negative sign is there because cosine on this side is negative, okay? If we look at our triangle and we call this theta, adjacent is 2, hypotenuse is 3. This side is going to be the square root of 3 squared minus 2 squared. Pythagorean theorem, right? I just jumped right to the chase of what's important. This squared plus this squared equals this squared. And so this one is going to be the square root of this squared minus this squared. So square root of 9 minus 4 is 5. Okay, I agree. Okay? So that's the square root of 5. Now what's the sign? The sine of theta then is going to be opposite square root of 5 over hypotenuse 3. And in quadrant 2, sine is positive. So this is the number they're looking for.
Why is,
That was simple.
oh, no, never mind.
What's the sign?
So thanks, Megan, for reminding everybody. Tomorrow I'll be looking at this. Oh, I'm sorry, I looked at the wrong one. I said 13 to 35, I was looking at 19 to 53. Let me look at that again. We'll pause for a moment. Okay, listen please. I did look at it to see if I should change it due to time, but there's really, all that stuff is kind of important. And so I realize you're going to have homework tonight. I apologize for that, but get it done. And tomorrow we'll make sure we get through things quicker, and you'll have a lot more time to work. Okay? We won't be copying down our notes for a cheat sheet or any of that stuff. So
30s already.
19 to 53 odds. I think 18 problems.